Good morning to all of you.
Good morning, sir.
Good morning, sir.
Good morning. So, are there any questions, doubts?
Hello, sir.
Yeah.
Sir, I have a doubt on this gap. Basically, in the last class, you defined gap U3 minus U4 greater than G, then the gap is closed.
Yeah.
So does whatever G value we are saying, is it like some penetration which is happening, or
No, it is not the penetration. It is the initial gap between the two nodes, no?
so when this gap will be closing, still there will be some distance between the two nodes. Sir, is it like that? I'm not able to exactly understand.
No, the distance when the gap is closed, the distance between these two nodes would be 0. When see initially there is a gap, so you have U3 and the U4 on the other side. So initially that gap I have taken as G. And then when you apply the load, then U3 is increasing. So U3 will be when there would be a load F star when U3 will be equal to G and U4 is 0. So that time the gap will be closed. And then subsequently there would be deformation at node 4 also. So then subsequently U4 will also be non-zero. But the values of U3, U4 will always be such that U3 minus U4 minus G equal to 0 when the subsequent deformation happens.
Okay, sir. Actually, I was thinking about U3 as the net displacement from the reference.
Yeah, so U3 is the net displacement from the reference only, from the initial position.
Okay, sir. I got it. Yes, sir. Understood.
Now, what we are saying that the U3 minus U4, when the gap is closed and the further deformation is happening, so U3 minus U4 will be equal to G. That will continue to remain as G, U3 minus U4.
Okay, sir. Okay. Thank you, sir.
Hello, sir.
Yeah.
Sir, if one force is acting on 4-5 beam, means if two pieces of beam is there, means 4-5 node, means in that section, if one force is applying in opposite direction to F.
Yeah. Okay.
Then in that case U3, if they will the displacement will approach to towards each other, means that U3 and U4. At that time, U3 minus U4 is if it will be less than G also, it will be they will contact each other.
No, you will have to still talk of U3 minus U4. If that is equal to G, then only the contact will be there. So of course U3 minus when U4 you are doing, U4 is negative, so it will become actually, if you take just the magnitude, it would be U3 plus magnitude U4. That would be equal to G.
Okay, means U3 plus U4 equal to G at that time.
U4 is negative, so you can still write it as U3 minus U4 minus G equal to 0. But U4 would be negative, so actually it would be getting magnitude of that would be getting added.
Okay. Yes, sir.
Yeah. So are there any other question, anybody? Okay, so if there are no questions, let me start. So we are continuing with the contact mechanics. Yeah, it's not writing in my screen, so let me close and open. Hello, is my screen visible? Hello, is my screen visible? Hello, is my screen visible?
It is
Okay.
visible.
So I think I had given you that example for you to work out. So I will just do an initial portion of that, and of course I expect you still to do that. So we are continuing with the contact mechanics. So the second example I was talking about was this beam example. So one side of the beam is fixed, and this is x coordinate, this is y, and there is a downward force q, and the beam is just discretized into one element. The flexural rigidity is ei, and this is node number 1, this is node number 2, length of the beam is small l, and then we had said that there is a spring below node 2. This stiffness of this spring is k, and this is, let us say, node 3, and this gap is between this node 2 and 3, the lower part of the beam at 2 is g. So this is what the problem I had given, and the actually analysis is similar to what we discussed the first problem. So now if you now look at the solution, so let me just give you some few steps. So initial possibility is that load Q is such that the node no, the beam at node 2 does not touch the node 3. So we can say that node 2 does not come in contact with node 3. So that is one possibility. So for that, no, you already know the basically the element level governing equation for beam. So because the first node displacement and rotation both are 0, so after we eliminate that, the degrees of freedom corresponding to node 1, so you will have the element level, the system equation after imposition of the boundary condition would be just the equations in V2 and theta 2. Theta 2 is of course dV by dx at node 2. So that would be from the beam element level governing equation. You get this after imposing the boundary condition. This will be equal to, the load Q is negative, so in the downward direction that is minus QL by 2, and we are using consistent load vector, so this is what you will have here. Theta 2 is actually dV by dx at node 2. So now if you solve this equation, so the solution will be, so this is after you take the element level governing equation for the beam, and beam is discretized just using only one element, and then you eliminate the first and second equation corresponding to V1 equal to 0, theta 1 equal to 0. So you get this equation, and if you solve this equations, we will get V2 is equal to minus QL power 4 upon 8EI, and theta 2 would be equal to minus QL cube upon 6EI. And of course, as you know, here V3 is going to be 0. V3 will remain 0. Now if we look at the magnitude of V2, so we need to look at V3 minus V2. V3 is 0, V2 is negative, so minus minus becomes plus. So now if we check this QL power 4 upon 8EI, that is V3 minus V2 value if we look at, So if this is less than equal to G, then the above solution is valid. Now let us say that just when the equality holds, so at that time the load is, let us say, Q star. So then Q star L power 4 upon 8 EI will be, let us say, equal to G. So from this you can say that Q star will be equal to 8 EI G upon L power 4. So corresponding to this load Q star, we will have V2 star. So V2 star will be simply minus G. When the Q is equal to Q star, V2 star is going to be minus G. And theta 2 star, if you work out, put the values, this will come out as minus 4G upon 3L. That is, in this expression, you put Q star, value of Q star over here in this expression, so you will get theta 2 star. And at this point, at this load Q star, V3 star will be just equal to 0. So now if we look at the case 2, when the load Q2, case 2, that Q is greater than Q star, and if Q is greater than Q star, then node 2 is going to be in contact with node 3, and there would be displacement of node 3 also, and there would be contact force between node 2 and 3. So now if you look at the governing equation for this case 2, so now in this case, let us be talk of additional load from Q star. So let us define that the additional load Q as Q dash, and Q dash is, let us say, Q minus Q star. Then the equation will be EI by LQ. The two equations, beam equation would be there, 12 minus 6L minus 6L and 4L square. This will be there. But then additionally we have equation for node 3, that would be the stiffness of node 3 is actually 0. So no, sorry, is capital K. So K into V3 dash is going to be actually equal to the contact force. So since EI by L cube is taken outside, so I can write here K L cube upon EI, so that when we multiply outside EI by L cube, we just get K. So this will be the equation, and this is the additional displacements of V2 dash, theta 2 dash and V3 dash, and this will be equal to load vector. So we have distributed load minus QL dash upon 2 plus contact force at node 2 would act in the upward direction, so that would be plus FC, and then Q dash L square by 12 would be there corresponding to theta degree of freedom, and at node 3 the load is going to be downwards, so it would be in the negative direction of V3, so minus FC. So this is going to be the equation here. So here you will see that now the forces, if you look at in the beam, so of course this distributed force Q is there, then here this FC is there, that is, and this is node 1 and this is node 2, and then here at node 3 FC is there in the downward direction. So for that, these are the equations. And now if you look at the unknowns are V2 dash, theta 2 dash and V3 dash and FC. So there are 4 unknowns and only 3 equations, so we need one additional equation. So that comes from the gap condition. So that would be V3 star, that is total displacement at node 3 plus V3 dash minus V2 star minus V2 dash, that is total displacement at node 2 V2 dash. This must be equal to G. So this is an additional equation, that is the 4th equation. And now we see that V3 dash is actually, V3 star is 0, and yeah, so you know that V3 star is 0 and V2 star is just equal to minus G, so that would be minus minus plus. So this equation will give you V3 dash minus V2 dash equal to 0, or V3 dash is equal to V2 dash. So now out of these three equations, if you look at, if we take the from this set, from last, no, we take the last equation. So from last equation we will have, basically if you look at k into v3 dash, this side, k into v3 dash is equal to minus fc. So now you can write fc in terms of v3 dash. So we will be having fc equal to minus k into v3 dash, and v3 dash is equal to v2 dash. So you can say minus k into v2 dash. So now if you look at the first and second equation from the same set, first and second equation, these steps are exactly similar to what we have already discussed for the rod truss problem, rod problem. So now if you look at fc is minus k into v2 dash. So what we can, and we are taking first two equations. So if you look at in this equation, fc is minus k into v2 dash. So we take this to the left hand side. So we will become plus k into v2 dash. So it would be getting added, actually no, with this term 12vi upon l cube. So you will add with that. So then these last two, the first two equations will become, this 12vi by l cube is already there, plus as I said, when we take fc to the minus fc to the left hand side, we will be adding k here, and then minus of course 6ei by l square is already there, and minus 6ei by l square, and then this is 4ei by l. So this into v2 dash into theta dash will be equal to, then the right hand side you have minus q dash l by 2 and q dash l square by 12. So now these are the two equations in v2 dash and theta 2 dash. So you can just solve for v2 dash, and you can solve no easily this equation v2 dash and theta 2 dash, and then the final solution then will be v2 will be equal to v2 star plus v2 dash, the sum of these two, and theta 2 will be equal to theta 2 star plus theta 2 dash, and of course v3 will be v3 star plus v3 dash. So once you get v2 dash, you will get v2 dash is v3 dash is equal to v2 dash. So from there you will get v3 dash. So that will be the total solution. So this is how the other methods which we discussed in the first example, you can try similarly. I think I'm not going to repeat all the things. They are now similar. You will get an idea how to do the various things here. So now this is no, you should of course solve this problem using other methods which I have discussed in the other lecture. So you should of course do that. So like this, 1D problems with this kind of contacts you should be able to solve using any other methods we discussed in the last lecture. So now I'm going to actually start with a general contact problem. So these two were the specific examples. So now I'm going to discuss general contact. So first thing is, in the terminology of contact mechanics, we have two or more bodies coming in contact. So we actually assign some name to these bodies. So one body is known as contactor or slave body. So this is contactor or slave, and the other body is known as basically the target or master body. Target or, that is the nomenclature used in the contact mechanics. And now how do we decide which body to treat as contactor, which body to treat as target? So usually if one of the bodies out of the two bodies, if one of them is rigid, So rigid surface is always chosen as the target if you have one body as a result. So rigid surface is always chosen as a target. And if both the surfaces are deformable, when both the surfaces are deformable, then the choice is arbitrary. You can assign any one body as target and another body as contactor. The choice is arbitrary. So now this is the one thing. Then we have to define the normal at the contact point. So we need to because in the previous case the two examples we considered, we knew exactly which nodes of the one body is going to come in contact with the other body. So the nodes were known, the gap was known, but in general context we will not know which points of one body is going to come in contact with the other body. So we'll have to calculate that, and also what is the gap between the two bodies corresponding to those two nodes. So that also has to be calculated. So we need to do the contact. We need to identify the contact point and gap. So contact point and gap calculations. So first thing, if you look at, we will talk about the actually normal. So again the same two bodies, this is one body and this is the another body, and this is now the point. Let us say this is the contactor and this is the target body. So now the normal outward normal at the point of contact on the target body is, let us say, that is vector nt. So that is at this point, and similarly the same at the same point normal to the contactor is, let us say, nc. So at the contact point these two are going to be equal and opposite, and nt and nc are the normal at the contact point to the target body, and nc is normal to the contactor at the contact point, and they are unit vectors. So at the contact point we will have normal to the target would be equal to minus times normal to the contactor body. So first let's look at, before we can identify the gaps and the contact points, let us talk about normal. How do we get the normal? So normal to, we'll have to get normal to each body. So normal, and then there could be two possibilities. Let us say first we talk of 2D problems, and then we also look at how to get this normal for the 3D problems. Now 2D problem, let us say that at the contact zone we have some, the both bodies, contactor as well as target bodies, would be discretized into a certain number of elements. Let us say we look at the one element of either the target body or the contactor body. So let us say the surface is discretized, although it can be discretized in any of the 2D elements. Let us say it is discretized using 8-noded isoparametric element. So these are the corner nodes 1, 2, 3, 4, and these are the mid side nodes 5, 6, 7, and 8. And the coordinates are x1, y1, x5, y5. These are the coordinates x2, y2, x6, y6, x3, y3, and similarly for this x7, y7, like that. Similarly x4, y4, and x8, y8. These will be the points. And now let us say that we are talking about some point, let us say here. So So at this point, the tangent is, this is tangent and this is the normal. So let us say n is normal, and this is no, this tangent which I have drawn. Let us say that is vector t, tangent vector. And this element, of course, as you know, is isoparametric element. So this is mapped to a square in the natural coordinate space. So we have xi and eta. The nodes are same, or corner nodes and mid side nodes. 1, 2, 3, 4, 5, 6, 7, and 8. So now if you look at in this case, you will know the all the coordinates. So you will be able to write x coordinate of any point as a function of xi eta. So it would be in terms of shape functions ni xi, and similarly y coordinate would be expressed in terms of xi and eta. That would be summation ni yi. Summation is I going from 1 to 8. The summation I going from 1 to 8. So this is what no is the interpolation. But now for the contact, we are interested on the boundary. So along the any boundary, if you look at, let us say we move along the boundary, and let us say the parameter no length along boundaries, let us say that coordinate is a, and we are actually going to take that in the natural coordinate. So this is a in this direction, in this direction, and in this direction. So we are measuring a like that. So along the boundary, because one of the natural coordinate, either xi or eta, would be known, so the other natural coordinate would be variable. So you can write the x and y coordinates along the boundary in terms of a single parameter, either xi or eta, depending on which boundary we are going. So along the boundary, we'll have the coordinates as a function of, let's say, parameter a. So x coordinate as a function of parameter a, y coordinate as a function of parameter a. So here a is a parameter varying along the boundary, is a parameter varying along the boundary. So now, for example, how do we identify this parameter a? So if you are going along boundary 1, along 152, this boundary, so then you will know here in the expression for x and y, you will put basically along 15 eta is equal to -1, and then the parameter a would be actually xi. Now if you look at along boundary 263, so there you will see xi will be equal to +1 and parameter a would be eta. And if you look at the boundary 374, so along that boundary you see eta equal to +1, and a will be now the direction of a, and no, so the a is in this direction, as I indicated this arrow over here, whereas xi is in this direction, so a would be minus xi. And if you similarly are know the contact boundaries along the 481 edge of the element, so then xi is going to be -1 and a would be equal to minus eta. So this is how you will identify, depending on the contact boundary, you would identify that which edge of the element is that contact boundary, and then you would be able to identify the parameter a, either xi or eta or minus xi or eta, depending on which edge of the element is that contact edge. So once you have defined that, then you can actually now define the tangent vector. Tangent vector at any point, at any value of parameter a. So let us say denote that by, I am denoting the vector by underscore. Now in this discussion, what I will do, I will denote the vector by 1 underscore and a second order tensor or a matrix by with 2 underscores below that. So now t will be equal to, now say the unit vectors along I and j, along x and y are I cap and j cap. So when you are finding out the tangent vector over here, this tangent vector, so this would be dx upon dA I cap plus dy upon dA, j cap. So basically dx I cap dy j cap, that's what you have. So this will be dx upon dA I cap plus dy upon dA j cap, and this should be unit vector, so we divide by the magnitude of the vector. So the magnitude of the vector is dx upon dA whole square plus dy upon dA whole square. So this is how you get the tangent, and once you have the tangent on the boundary, you can identify the normal. So normal is going to be perpendicular to the tangent, so then its unit vector is going to be dy by dA I cap minus dx upon dA j cap divided by the magnitude. So the magnitude is same, my dx by dA whole square plus y upon dA whole square. So this is the normal vector. So this is how you identify the normal. This normal could be, if that element is of the contactor body, then this will be normal to the contactor. If that element is of the target body, then this would be normal to the target body. So you would be able to get NC and NT using this expression. Now if you look at the x component of n, so nx is, as you see, it is dy by dA upon square root of dx upon dA whole square plus dy upon dA whole square. And similarly the y component of n will be ny, which is minus dx upon dA divided by magnitude, so dx upon dA whole square plus dy upon dA whole square. So this is how you get the normals. So using this method you can get the normal for the target body, you can also get the normal for the contactor body, no, within an element, particular element. Now if the problem is a 3D problem, so then the contactor and target bodies would be discretized using 3D elements. So let us say 3D problems, how do we get the normal? So let me explain that. So now in case of 3D problems, if you look at the element is a 3D element, let us take an example of a 20 noded brick element. So this is x coordinate, this is y coordinate, and this is z coordinate, and then you have the element. So this is the element. This is the element in the physical coordinate space. So now if you look at the nodes, so these first I'm numbering these corner nodes. So let us say this is 1 2 3 4, then mid side nodes, so this is 5 6 7 and 8, then the nodes at the top, so let us say this is 9 10 11 12, and then mid side nodes, so 13 14 15 and 16, and then these nodes, so this is 17, this would be 18, this would be 19, and this would be 20. So this is 20 noded brick element in the physical coordinate space. This will be mapped to the natural coordinate space. In the natural coordinate space, the element would be a cube. So this is the element. Now the nodes are going to be these nodes. Now you can number similarly these nodes. And then the mid side nodes. So numbers are, this is 1 2 3 4 5 6 7 and 8, and this is 9 10 11 12, then this is 13 14 15 16, this is 17, this is 18, this is 19, and this is 20. So this is the element. Now we want to identify the normal. So when this element is on the contact region, where it is coming in, either it's a part of contactor body or it is a part of target body, so we want to identify so now for this also you will have the coordinates of all the nodes, x1 x2 x3 xyz of all the nodes would be known. So x would be, let's say, function of xi, eta and zeta will be equal to summation ni xi, and the element could be 8 noded element, or it could be 20 noded element, or a 27 noded element. I have just taken this as an example. So this is I equal to 1 to 20. And similarly, y as a function of xi, eta, and zeta would be equal to summation I going from 1 to 20 and I yi, where xi, yi, and zi are the nodal coordinates, and similarly z would be function of xi, eta, and zeta would be summation I going from 1 to 20 ni zi. So yeah, these are the coordinates. Now in this case, the contact region, the contact surface is going to be a 2D surface. So if you look at the boundary of the element is a surface. So here the for the 2D problems, the the contact region is a 1D curve, whereas for the 3D problems, the contact surface is going to be a 2D surface. So if you look at the boundary surface, we'll have one natural coordinate would be specified for that boundary, and the other two are going to be parameters. So a boundary surface in this case for 3D problems is characterized by two parameters. And let us say those parameters are A and B. So that now depending on which surface you are, for example, let me take the surface, let us take one of the surface here. So if I take this surface, let us say to this particular surface, no this side, no this surface. So that surface is 2, 3, 11, 10 and 6, 19, 14 and 18. So it is give that surface which I am talking about. So let us say 2, 3, 11, 10, 6, 19, 14 and 18. So if we take this surface, so in this surface, if you see here in the natural coordinate space, the natural coordinates of course are, if you look at here, this is xi, this is eta, and this is zeta. So if you'll see that along this surface, xi is equal to actually unity, xi equal to unity, and let us say parameter A is eta and parameter B is zeta. So the parameter A and B are eta and zeta, and xi is equal to unity for the surface. So on that surface, you will have x as a function of parameters A and B, y would be function of parameters A and B, and z would be functions of parameter A and B on any surface. So what we can actually do is we get the two tangents to the surface at any point. So let us say if this is the surface, at some point on that surface, let us say we have one tangent which is vector v1, another tangent which is vector v2. So here v1 and v2 are tangents to the surface, and this surface could be of contactor body or target body, tangents to the surface. So vector v1, if you look at, it would be equal to, it's not a unit vector here I am writing, so this would be del x by del a, because now x, y, z are functions of two parameters, so the partial derivative come into picture. So del x by, we will have del x by del a I cap plus del y by del a j cap plus del z by del a into k cap. So this is vector v1. By varying a, we get vector v1, and by varying b, we get vector v2. So that would be del x by del b I cap plus del y by del b j cap plus del z by del b k cap. So you can, because x, y, and z are functions of parameters a and b, so you can get these derivatives. So therefore you can get the vector v1 and v2 which are tangent to the surface. Yeah.
Sir, we will get tangent, infinity tangent we can get, no?
Yeah, we can, but we are taking one tangent by varying a, another tangent by varying v. So those would be specific tangents. Yeah, we can have a infinite number of tangents, but we are taking two normal vectors v1 and v2. So V1 is along by varying A and V2 is varying by parameter B. So the parameters could be either pair of eta and zeta, or can be xi and eta, or can be xi and zeta. So depending on the surface. So those could be the parameters. So these would be two specific tangents. So then the normal to the surface, that is what we are interested in. Normal either to the contactor body or normal to the target body. We will get that as normal to these two vectors. So V1 cross V2 and divided by magnitude of these. So V1 cross V2 magnitude. So from this we will get the normal vector. Now if that element belongs to contactor, then this would be normal to the contactor. If the element belongs to target body, then this would be normal to the target body.
Hello,
So
sir.
this is how, yeah, yes, tell me please.
Sir, this V1 and V2 need not be perpendicular to each other, right?
Yeah, actually it is not necessary. You are right. We are just taking two vectors in the tangent on the plane tangent to the surface at that point, and then we are finding out normal through their cross product. So yeah, it is not necessary that V1, V2 are perpendicular to each other. That's right. So now, so once we get the normal,
Yes, sir. Sir,
yeah,
but sir, natural coordinate it will be perpendicular to each other. Natural coordinate.
natural coordinates are perpendicular, but it is not necessary that when we take the del x by del a and this vector and this vector, so it is not necessary that these two will be uh, perpendicular to each other. Yeah, this they could be, but it is not necessary.
Sir,
But
this
of course,
V1, V2 is it is in natural coordinate or in physical coordinate?
they will be in they are functions of natural coordinates, because x, y, and z are functions of natural coordinate, two parameters a and b, which are two of the natural coordinates.
Okay. And in this case, it is perpendicular to each other. In this case.
Yeah, I have the way I have sketched here. They are shown as perpendicular to each other.
Okay. Sir, means if we will formulate the V1 and V2 in natural
Yeah,
coordinate, they will be perpendicular to each other always in natural coordinate.
yeah. We are taking one vector along one of the natural coordinate, another vector along another. So then it would be, but here since it is x, y, z coordinates which are involved here, so change of x, y, and z coordinate by changing parameter a, change of x, y coordinate by changing parameter b. So these need not be perpendicular.
Okay,
So
sir.
we are, since we are taking physical coordinates x, y, z, which are functions of parameters a and b, which are two of the natural coordinates. So these need not be perpendicular.
Okay.
Yeah, but only requirement for the calculation of this normal is that these should not be collinear. That's the only requirement. And if so, we will always get the normal to the body. So now, how do we get? So let us say if we have a we take a point in the contactor body, and then how do we get the corresponding point on the target body? So now after normal, let us talk about this. How do we calculate this? So point in the target body corresponding to a so point in the target body corresponding to a point in the contactor body. So if we choose one point on the contactor body, and then we want to find out which is the point closest to the which is a point on the target body which is closest to the point on the contactor body. So point in the target body corresponding to a point in the contactor body. We have to identify these pair of points. So since we are choosing one particular point on the contactor body, so let us say that that point in the contactor body is given by, let us say that point on the contactor body is P, and the superscript is denoting the contactor, so XPC, YPC and ZPC. So let us say this is the point, and now we want to get the point which is closest to this in the target body. So let us say that the corresponding point on the target body is, let us say that the corresponding point on the target body and that point is going to be function of parameter. Let's say if you're talking of 2D contact problem, I mean 2D bodies, then it would be this coordinate is going to be function of one parameter. If it is a 3D, the bodies involved are 3D bodies, the discretization is 3D, so it will be function of two parameters. So here I'm writing for 2D just a single parameter, so point on the target body is XTA, YTA and ZTA. T is superscript T is for target and A is parameter. And if this is a 3D problem, then this will be function of two parameter A and B. So you will have XTA comma B, YTA comma B, ZTA comma B. So you would have like that. So now
Yes,
you have to, yeah.
Insert 2D Z will come.
Yeah, Z can still be there because the bodies can be oriented in arbitrary position, no?
Okay.
So yeah, Z can still be there. Yeah. So it is not necessary that whole of the the XYZ are aligned with, let's say, mid plane of the body. So it can be there, it may not be there, depends on the problem, but in general it can be there. So it may be only the two coordinates you might have to deal with, or sometimes you may have to deal with three coordinates because the orientation may be arbitrary. And if it is a 3D problem, then XTA comma B, YTA comma B, ZTA comma B, it would be like that. So we have to actually find this A so that this point is closest to this point on the contactor body. So now how do we find A? To find to find A, we minimize the distance between the 2 points, the point on the contactor body and this particular point on the target body, which is a function of A. So minimize square of the distance. So let us say L square, and L square you can write minimize as AXT, that coordinate of the target body, minus XPC whole square. You are writing basically the distance, plus YT minus YPC whole square plus ZT minus ZPC whole square. So you are basically going to minimize this distance. So now for 3D it would be L square would be function of A and B. For 2D it would be function of only A. So now because we have to minimize this, so we use the first order necessary condition. So to get parameter A for the point on the target body, we just do this, dl square upon dA equal to 0 and solve for A. For 3D you will get two equations. You will have dl square del, you will have two equations basically, del L square by del A equal to 0 and del L square by del B equal to 0, and then you solve for A and B. Solve for A and B, A comma B. So depending on the problem. So once you have then done this, so you have chosen a point on the contactor body, and then you have found through this process point closest on the target point, closest to the target contactor point in the target body. And once you have done this, then you can do the gap calculation, that G. So now next is gap calculation. How do we calculate the gap? So the gap is Gap calculation G is we know one point on the contactor body and the corresponding closest point on the target body. So we want to calculate G gap as the sign distance. So this G will be equal to dot product of the vector from target body to contactor body with the normal to the target body. So that will be written as XPC minus, now that point on the target body is, let's say, Q, which is the closest to point P on the contactor body. So this is the vector I cap plus you will have YPC minus YQT J cap plus we will have ZPC minus ZQT. Superscript T is for target into K cap and dot. Now you take the dot product with normal to the target body at that point NT. At point Q you find the normal to the target body and you get this NT, and then take the dot product, you get the basically the gap between the two. The we are known as contactor body and the corresponding closest point on the target body. What is the gap? And this gap vector is a sign distance from target point Q to contactor point P. So it's a vector in that direction because NT is normal to the target, so it would be towards the contactor body. So now depending on the situation, you could have two possibilities. That is, if let us say G is greater than 0, then gap between there is a, that means there is a gap between the bodies. There is a gap between the bodies, and now let us say if G less than equal to 0, then there is a interpenetration. One body is penetrating on the other, interpenetration. And if of course G equal to 0, the bodies are just touching, bodies are just in contact at that point. Yeah, so now, so this is how now you calculate the normal, and then you, how do you calculate, you take 1 point. No, so then what you actually have to do in the actual scenario, if you're using packages, so for every point on the contactor body, it would be identifying what is the corresponding closest point on the target body, and it would establish the contact pairs. So now let me take an example of calculations, all these calculations. I will only, this example is taken from Asgar and Bhatti. So you can go through that, but you, yeah, so basically you should be able to do these calculations. So let us say this is X and Y, and 1 point, let us say the target contactor body is this. This is the contactor, and this is discretized using 8 nodes. So these are the nodes here, and node numbers are, let us say, I'm numbering in this fashion, so accordingly you have to take the shape functions 5, 6, 7 and 8. So this is the contactor body, and then at some distance we have another target body. Let us say this is the target body, and the nodes on this body are, these are the nodes, and they are numbered as 9, 10, 11, 12, 13, 14, 15 and 16. So now you will obviously write, no, this is a 2D problem, both they are 2D problems. You will only work with 2 coordinates. X is a function of xi and eta, you will write that as ni into xi, and y as a function of xi eta, you will write that as ni yi. And you need the all the coordinates. So the coordinates are the coordinates of all the points. Let me write the here. So let us say we have node number here x and y, and so let me write for node 1 the x coordinate is, so you, so that now I'm giving these values so that you can work yourself, 7487, and this is 24.7 847, and then 2 is 34.3275 and 6.82816. So all are written 6 digits in 6 digits, as you see. Node number 3 cox and y coordinates are 32.3358, and this is minus 13.3939. Node number 4 will be mean of 3 and 5. So x3 plus x5 by 2, y3 plus y5 by 2. So yeah, this is now let us say again, let me list here node x and y. So node 5, x coordinate is 46.194 and y coordinate is minus 19.1342. Then 6 is 49.0393 and 9.75452. Node 7 coordinates are 35.3553 and 35.3553. And the coordinates of node 8 are mean of 1 and 7. So x1 plus x7 by 2, y1 plus y7 by 2. So these are the coordinates of the contactor body, nodes of the contactor body. Same way we look at the target body. So node x and y, the coordinates are node number 9, 65.3284 and 46.7878. Node number 10, the coordinates are 61.345 and 6.34368, and 11 are 80.5025 and minus 29.4975. Then 12 coordinates of 12 are mean of 11 and 13, y11 plus y13 by 2, and coordinates of 13 are 94.647 and minus 15.3553. Coordinates of node 14 are 80 points. So you need lot of information as you see as the input. So 10.2455, 15, 83.806 you can know, so that you can check the calculations. 39.1342 and 16 are mean of 9 and 15. So x9 plus x15 by 2 and y9 plus y15 by 2. So yeah, these are the coordinates. As you see, the coordinates of both the contractor body as well as the target body. This is the target body. So now if you look at the calculation, so let us say we choose 1 point, on the, we'll have to find out the normal to the contactor, we have to find out normal to the target body, we have to find out, choose 1 point on the, let's say, contactor body and find out the corresponding point on the target body. So these are the things you need to do. So now let us say this face is going to be in contact with this. So if we look at the along the boundary 567, which is basically the boundary of contactor body. So if you look at along boundary 567, so along that boundary, because what you are mapping with is this is mapped to the natural coordinate edge parallel to xi axis. This is mapped to eta axis. This is again mapped to xi axis. So eta would be equal to +1 along this boundary. Eta would be equal to 1, and A will be minus xi. So now based on this, if you calculate the coordinates on the contactor body, so xc, there will be function of A. Now you have from this expression, you have x as a function of xi eta, y as a function of xi eta, and in that you put basically in this expression you put eta equal to 1 and then xi equal to minus A. So you will get xc as a function of A. Xi equal to minus A in that expression, eta equal to 1 and xi equal to minus A in that expression, so you will get xca. So if you do that calculation, it turns out that this comes out as minus 8.2646 A square minus 5.41932 A plus 49.0393. So this is how this XCA will be, and similarly YCA on that edge. This edge we are talking about, this edge. YCA comes out as minus 1.64393 A square plus 27.2448 A and plus 9.7545. That is how YCA is coming out. So now once you have got these values, you can now, if you want to get the normal to the contactor body, so you calculate dxc by dA, you differentiate and get the values, you get dyc by dA. Now you have got this, so differentiate and get this value. Then calculate the magnitude. Let us say I am denoting that as jc, and that you will calculate as dxc by dA whole square plus dyc by dA whole square. So you calculate this, you will get the value for this. So then finally you will see where the formula we have already written. You will see that. Yes, tell me please. Yeah.
Along the boundary 5, 6, 7, shouldn't it be xi equal to 1 and A
So
equal
see,
to
the mapping is done, the how the map, it depends on how the mapping is done. So if you look at in the natural coordinate space, so the mapping for this is done like this, so that this is node 1, this is node 2, this is 3, and then this is 4, this is 5, this is 6, this is 7, and this is 8. So that is how now when I'm saying this 5, 6, 7, so in that eta equal to plus 1 and A equal to minus xi. So the mapping is done like this. It depends upon how you do the mapping. No, when you write this nixi and niyi, how you, in which order you take the shape function and the coordinates. So it depends on that. So in this case, the mapping is done like this. So that is how we are saying, yeah, along the edge 5, 6, 7, eta is 1 and A equal to minus xi or xi equal to minus 2.
Why we are taking xi is equal to minus A? We can take xi is equal to A as well.
No, because we are no, with this mapping, this element is mapped to this element in the natural coordinate. So when we are moving along 5, 6, 7, so we are going along this edge. Here you see 5, 6, and 7. So we are moving in this direction. So that is why we are taking, because xi is in this direction, A is in this direction. So A equal to minus xi. Is that clear?
Okay, sir.
Yeah, because boundary coordinate is taken in the same direction. So now if you finally do the calculations, you will get then nxc, the formula I have already given you. So you will calculate nxc, yc, you should do all these calculations yourself. You will get nxc, and similarly now if you look at the target body, that edge, the contact edge is going to be this 9, 10, 11 from here. 9, 10, and 11, the mapping is again done. 9, 10, 11 is mapped to basically this edge. So now if you if you look at the mapping for this case, 9, 10, 11 is corresponding to this edge, 11, 12, 13 is this edge, and 13, 14, 15 is this edge, and 15, 16, 9 is actually this edge. So for this, when you look at target body, you will have edge is 9, 10, and 11. So eta would be equal to minus 1 and A will be equal to xi. So in the expression for x and y for the target body, you put eta equal to -1 and xi equal to a. So you will get basically these functions. I'm just mentioning what are the steps, the calculation you should do yourself. Look at in the book also, you can have a look at it. The calculations are given over there. So xta you will get as a function of a, and similarly you will get then yta from this. Then you will be able to get xt by dxt by da from this, and dyt by da you will get from this. And once you have get this, then you calculate the magnitude for this. So that is dxt by da whole square plus dyt by da. Yeah, so you will get this dyt by da whole square, and then you will be able to calculate in similar manner the normal to the target body, and this would be dyt by da upon jt. We have given already this formula, and nyt will be equal to minus dxt by da divided by jt. So once you get these, then you calculate the, let us say we choose one point on the contactor body. So let us say we choose 0.6 on the contactor body. So corresponding to 0.6 on the contactor body, point on the target body would be point on the target body. How do we get that? So we have said that minimize the distance L square, which is the minimum of distance between the 0.6 and some point with parameter A on the target body, and from this you will get dl square by dA equal to 0. Solve for that, you will get the value A, and A comes out here now if you do all the calculation 12513. That is the value of A which is coming out from this. And then if you look at the point on the target, so xqt comes out as 60.5768 and yqt comes out as 11.1525. So you must do all these calculations and at this point, if you look at say at 0.6, we can calculate the 0.6 is on the contactor body and point q is on the target body. You have got the corresponding A, so you can calculate the components of the normal vectors. You will get nxt will be coming out as minus 0.992739, and nyt of normal to the target body at the point q comes out minus. Now you put the corresponding value of A and get the nxt and nyt. So 120288. And similarly at 0.6, the normal to the contactor nxc component is coming out as, it is going to be opposite of this, so 2739, and nyc will be 0.120288. And from this, if you do the gap calculation using this formula, which I have listed over here, this formula for the gap calculation, so you would see finally a gap G comes out as 11.622. So yeah, I think I want to stop here, and if you have any doubts and questions, you can ask.
Sir, will this gap should not be equal to the minimum distance between 0.6?
Pardon?
Sir, will this gap should not be equal to the minimum distance between 0.6
it would be
and...
actually, it would be equal to the minimum distance between 0.6 and the corresponding point on the target Q. So it would be that, but here we are calculating using this relationship. We are calculating this as a signed distance. So this may turn out to be positive, negative, 0. So it will tell how the gap is calculated. So we are using this formula rather than taking basically L directly, because L could be positive, no, will not show whether it is positive or negative, whether there is a gap between the two bodies or there is a interpenetration. So from this formula we will get that information. So that is why we are calculating G, and of course this will be equal to the distance. Yes.
Okay.
Yeah.
So you have taken a vector xp minus x.
Yeah.
Can you
So
go to the above formula
yeah.
of where you have dotted with n?
Yeah. This one. Yeah.
Yes, sir. So you have taken a vector between those two, among those two nearest points, right?
Yeah, nearest point. So point P is on the contactor, Q is on the target. So this vector is written from point on the target to the contactor. So this XPC minus XQC I cap, this vector would be directed from target to contactor. And then this NT is also the normal to the target. So that is why if the G comes out as positive, means it is a gap. If G is negative, this is a interpenetration of the bodies.
Sir, but xp and xq, these are the these are the points at already at minimum distance, right?
Yeah, right.
If they are already at minimum distance and we are taking a component along the tangential direction, so
Normal, not normal to tangent, not
normal
tangential.
to target
Normal.
body, huh?
Yeah,
Normal to
normal to
target
target.
body.
Yeah.
So will it not change the value of that minimum distance?
No, it will not, because
Because
you
we
are
are
taking
taking
vector
component.
from Q to P, and then you are taking the dot product with the unit vector, because NT is a unit vector. So when you take the dot product, it will give just the distance between Q and P.
Okay.
Yeah.
Hello.
Yeah. Yes, please.
Sir, so after finding this nx and ny,
Yeah.
so do we need to write the normal vector also, or should we leave the answer at this point only
No,
after
you have to
finding?
also write the normal vector. No, you have to write normal to the contactor. You have to write normal to the target. Of course, they are equal and opposite, but you'll have to write the values of normal, because these unit normal vectors, the gap G, all these things would be needed in the element level governing equations when we are considering the contact. So when we will be writing the element level governing equation for the target and element level governing equation for the contactor body, all these will be appearing in those. So we need these normals on the contactor and target at different points actually.
Okay, sir.
Yeah.
So we will have to do this calculation for each point on the edge 567, right?
Yeah, we have to do for each point. Yes.
Okay. One more thing, like
Yeah.
we have taken one specific point at 567. Can't we take the means a variable point at 567 and variable point at 11, 9, 10, 11 as
Yeah,
well? Because
we can do that also. Yes, we can do that. So then you have know the parameter, you can say AC for the contactor body. So the coordinates of the contactor body in terms of parameter AC, and you can have parameter AT for the target body, and you can find out corresponding to point at AC on the contactor body, what is the point, the value of, let us say, AT of for the contact target body. You can do that. Yes.
but here AC and AT are same only, no? Because
No, they will not be same. No, they can be, in general, they can be different. In general, they can be different. In specific cases, yes, they can be same. Values, no, values wise they could be same.
okay, sir.
Yeah. Like for example, here when I have taken this example, so for point 6, because along this point 6 you are having this A equal to minus xi. So actually value of xi at that point is going to be 0 in fact. So this, you will see that AC equal to 0, and whereas for this for the target body, A is coming out as minus 0.12513.
Okay, sir.
Yeah. So any other question, anybody? So if there are no questions, I am stopping. Thank you all for your attention.